Hi everyone. So we're going to be talking about loops this week. And the subject of lecture 7 is going to be the basic loop structures. And then when we talk about lecture 8, we'll talk about some more exotic approaches that we can take involving things like inner and outer and folding of lists. But for now, the main topic of today's conversation is going to be do, while, and for. So those are the traditional loop structures in procedural programming languages. And even though Mathematica gives us alternatives, a lot of cases with function mapping and tables, it's still the case that loops are a powerful tool that we can use when it's not immediately obvious how Mathematica's existing structures work, and if we're trying to improve readability. And often when we're trying to do complicated operations that involve more than one condition being modified at the same time, the loop is the natural way of thinking about how to proceed. So when you're talking about a loop, you need to identify what the loop does and how it's controlled. So every loop has a body, which consists of the code that's being executed over and over again. And it's got some sort of controller that says how much the loop runs before it stops. So a do loop is the simplest type of expression because what we're going to have is the first argument here of a do loop is the expression that's going to be iterated. And often, but not always, that's a function of the index. And then a second part, which is the controlling step, which is the index set that we're running the do loop over. If we do the command print the prime I, where I runs from 1 to 10, we get a list that looks like, well, what did it do? It did this command, print the ith prime, and it started with index I, and it ran it over the set I from 1 to 10. I believe that we can actually modify this and make a step size in here, and then what will happen is it will start at 1 and it will go to 10, but it will have a step size of 2 instead. So the same sort of controls that we have over tables and ranges, we also have available inside an index set for a do loop as well. Of course, often the things that we do with a do loop can be replicated in other ways. So for example, mapping the command prime onto range 10 gives you the same kind of answer as running a do loop where you're doing the print step. The difference being that the do loop is actually printing those to output, and the prime generation here, which is making a list, isn't. So another feature of loops that turns out to be useful is if you run a loop, even if it doesn't terminate or the calculation time gets too high, if you include a print step in your loop, then even as the loop runs, it will be producing output. Whereas if you try to do a statement like this, which has to execute all at once and finish before it actually produces an output, in that case, if you write something that doesn't finish or can't finish, you're not going to get any information out of it at all. And so frequently, if you need to do error checking or you need reporting on individual steps, you would really like to use a loop to do that. So one useful thing about loops is, of course, we don't have to include just a single statement in the setup for a loop. I can include lots of expressions in the body of a loop. And in the do loop and the other structures we're going to be talking about today, the way you do that is you separate the expressions you would like to execute on each iteration with a semicolon. And so this particular loop that I've written right here, for every increment of the index set, is going to calculate all 3 of these expressions. So the example I've written here is a do loop that is indexed by I, so the index set is normal. But on the left-hand side in the body step, we've got 2 expressions being computed now. So the first thing that happens is we assign the variable j to be the value of the ith prime, and then we print the index that we're at and the j that goes with it. So this is very similar to using a table with 2 entries to produce a list. But now, as we go through step by step, when I is 1, the first prime is 2, the second prime is 3, the third prime is 5, and so on. And so again, the fact that we can include this print step is an argument for the utility of even a simple structure like a do loop. So let's consider the formula n squared plus n plus I. And let's suppose that we want to find the number of consecutive primes produced by this formula for values of I, say between 1 and 10,000. Well, the reason that this formula is interesting at all is, as Leonard Euler discovered, if you run this command where I is equal to 41, you get that the first 40 integers that you plug into this formula produce prime numbers. So that is, if you actually put a 1 into here, so 1 squared plus 1 plus 41 is 43, and that's prime. If you put in the 2, you get 2 squared plus 2, which is 6, plus 41, which is 47, which is also prime. And you can continue doing that for values of n between 1 and 40. And so there are 40 consecutive primes produced by this formula. And you might wonder, if you vary the value of I, can you get more primes in more consecutive primes? So we can actually build this into an answer to that question by using a do loop. And what we could do is we could increment over not 41, but we could have the do loop increasing a value of I that's set up right there. So one way of thinking about that would be, we're going to use this list building trick. So the particular list building trick that I'm interested in using is this idea that I can always extend a list by taking A and unioning it with a new list and then feeding all of that into A. So just as an example of what I mean by that, if you took the set, let's suppose that you let the set A be equal to a set consisting of the element 1. And then you took A and you set it equal to the union of A with the set 2, 3. Well, now you've got a bigger set, because what that step does is it takes the 1, glues in the new elements, and reassigns it to A. And this is a way that inside of a loop, you can actually build up a set. So the answer to this question, which is, can I make more consecutive primes by varying the value of I? Well, we can investigate that with this idea of recording for ourselves what the number of primes produced by a given index was. So let's actually do it. That's not supposed to be a joke about the do there. I did that by accident. So what we're going to do is we're going to take the expression that we did right here, all of this, because remember what that does is that tells us how many consecutive primes that formula produced with a 41 in the constant spot. So what we'd like to do is to do that expression, but now I don't want a 41 here, I want an I. And the do loop is going to require that we take an index I and we run it, for example, from 1 to, I don't know, 10,000. Let's make it more reasonable for now. Let's just do 1 to 100. So if we do this, what's going to be happening is we're not going to get output. Nothing has been stored here, right? Nothing has been printed. It's just run. So I guess I could print this. Well, if you do that, you get this list of individual sets here. For the value of I equals 1, we get 4 consecutive integers. For I equals 2, we get 1 consecutive integer. For I equals 3, we get 2 consecutive integers. But that's not very useful, because now I've got this giant list of outputs, and it's not easy for me to figure out what the maximum and minimum of that list is. Instead of printing, what we should be doing is building up a list. And so this is where we're going to use this unioning trick. So we're going to start by initializing a set A to be equal to the empty set. Then inside here, what we're going to do is we're going to let A be equal to the union of A with all of this stuff. And then when we're done, if we actually look at what A is, now we have a list of all of the outputs that were possible. So I see here, 40 consecutive numbers right here. So what is this loop actually produced for us? What is this set A? Well, these are the possible consecutive primes that we get for all the different values of I between 1 and 100. And you'll find actually that if you put even a larger number in here, you don't get a materially different set. In fact, 40 is still the largest number. Now, what this does not tell us is which I value was the I value that produced that number 40, or if there's more than one of them. And if you actually wanted to look at a list that we built like this, but not have it turn into a set. See, the issue here is that we've treated A as a set by using union, which means it's dropped all of the repetition and it's gotten rid of the order. If instead we want a list so we can associate the I value that we started with the output, instead of using union, we should use append to. So now I'm going to reinitialize an empty A. Now if I run this set and I look at what A is, now I'm going to get a list of all of the different possible outputs that this produced. And what this list means is Right here, we had 4 consecutive primes, 1 consecutive prime, 2 consecutive primes, but with the advantage that we actually know which index produced that output, because this is the index corresponding to I equals 1. Okay, so we've run our loop, and we have a list now where the index of each entry on this list is telling us for that value of I, when we put it into the formula, how many consecutive primes were produced. The first thing we don't need here is the extra braces around the numbers. So it's not unusual when we're working with append to or select to have lists of lists that we don't want. We already know how to deal with that because we've seen a lot of flatten already. So we'll flatten A. And now we have a list that has lots and lots and lots and lots of numbers on it. And so the first question we might have is, are there more numbers besides the 41 that we know produced this 40? How do I know? Because if I actually look at the 41st index, I get out the number 40. Okay, so let's go back and look at the whole list again. Are there other 40s in here somewhere? I mean, maybe. I guess I could scroll through and scroll and scroll and scroll and see if I can find something else. But it turns out there's an awful lot of 1s, 2s, and 3s in this list. So one way of actually detecting if you have more than one of those would actually be to go through and do an ordering on this list. And so what an ordering does is it resorts the list, but it actually tells you the index. That's what the ordering command does. Before we do that, though, let's look at sort. Let's just sort the list and see how many 40s there are, or if there's anything larger than 40. Okay, so that's not what we want. Maybe we want to reverse sort. Okay, so I have a 40 on the list, and only one 40. 140, 116, 112, 110, 3 7s, 6 6s, and so on. So which entry is producing that 40 and which entry is producing that 16? So one way that we can actually look to see what the index is that went with this, because notice, I don't actually know what the indices are that gave me the 40 or the 16 or the 12. If you want to find that, you can use a command called ordering. So if you do ordering on this, and you ask it for the first entry in the ordering, it tells you the answer 2. So what ordering is doing is sorting from smallest to largest. If you ask it for the last entry in the list, it tells you 41. So I is equal to 41 produced the largest entry on that list, which we already knew was equal to 40 because I could just write down the maximum of the flattened A, which was 40. Okay. What index produced the next smallest set of primes? So if I ask ordering to produce the last 2 elements instead, what it's given me is the 41 that I already know produced the 40, and then this 17 right here, which turned out to produce 16 consecutive integers. And how do I know that? Because if I ask flatten A, or just to ask A to spit out its 17th entry, I get 16 consecutive primes. And so the ability not only to find the maximum of a list that we've created with a loop, but actually identify which index it corresponds to is really important in a lot of applications. Okay, so let's move on. So while loops are controlled by a Boolean switch. And so in a while loop, what you've got is some sort of condition that executes the body as long as that condition produces a true. And as soon as that condition does not produce a true, then the loop stops. So it exits when it evaluates the condition and the condition is not true. So as an example of how you use a while loop, here's a very simple one. If we let n equal 1 and we say, oh, while the number n is not divisible by 17, increment n. So n++ is what's called an increment. So it takes the n value, increments it by 1, and then sets that equal to n, so that n is now 1 larger than it used to be. If you run this loop, you can print the final number here, which is 17. If you'd like to see what the loop is doing while it's running, we could take this print step and we could put it inside the loop. So the body of the loop now is not just going to be an increment, it's going to involve a print step as well. And if you do that, you're going to say, this is what's going on with the n variable inside the loop. is that it starts at 1, and notice it's printing a 2 because I've already incremented n by the time I print the first time. And the last number that n is equal to is the 17, because that's the first number for which this produces a true, because 17 is divisible by itself. And the not in front means that as soon as this is true, this is false. So it exits as soon as it gets a false. As an example of where you might use a while loop, let's look at the problem in the book, 7.6, of finding the closest prime number smaller than a given integer m. So a very simple input command is given in Mathematica by this input function, where the prompt that shows up when you run this is going to be this, given by whatever you have inside. So the input into the input function is whatever you want the prompt to be on the box that pops up. And then we have a while loop, a very simple one. And what the while loop does is it checks to see, is that number prime? If it's not prime, then putting the not in front turns that into a true, and it takes the initial number and subtracts 1 from it, and then checks again to see if it's prime. As soon as it is prime, the not prime q produces a false when it reads a prime number, and that stops the loop, and then finally we print the number. So if we run this, we can pick any number we want, I don't know, and this number on the bottom is the smallest number less than that is a prime number. That was actually remarkably fast for how many digits I typed into that number. Now, we can fancy this up using more variables. So we can print a more complete statement. If you know anything about scoping, what we can do here is we can introduce a local variable. So this is a variable that only exists within the construct module. And then we can use that local variable to use our initial variable m. So you notice up here, I've got this variable m, but we modified it while we were running the loop. If I don't want to modify the original variable, one approach we can take is to define a module. And the module has an internal variable, n, that I set equal to m. So now m is not going to be modified. Then I can run the loop on this local variable n. And then because I know what n is and I know what m is, now I can print out something that involves both m and n. Okay, so the module structure is a way of producing an object that has a local variable that is only used for the computation inside the module, and then it's released again once the computation is finished. So let's run this block, and what do we get? So let's pick an easier number. I don't know. That's pretty easy. And so the output here on this line corresponds to the output for the input step. I should have put a semicolon there to stop it. And then, what we've got now is a statement where I can print both the input and the output that the loop gave corresponding to it. So I can print, complicated fancy statements like the smallest prime less than 123 is 123 Okay, oh. Gotta be grammatically correct here. Let's make sure we put a period on the end of our sentences. There we go. Okay. So this is kind of a more sophisticated approach to this, but built into the idea of using loops is that you might want to retain the initial information that went into initializing the loop and then continue on as you go through, so you can compare the end variable to the input variable. And there's lots of ways to accomplish that, but a module is sort of a high level way of accomplishing that. All right, so let's move on. For loops let you initialize the loop before it runs and then define an increment step that's outside of the body. So initialization is actually very useful when you want to run something over and over again without having to go back and re-execute like outside initialization lines. So here's a very simple for loop. If we start at I equals 0, that's the thing I'm initializing. So I have a variable I, and before I run the loop, whatever I was equal to the last time I ran it, it immediately sets it equal to 0. It runs the loop as long as I is less than 10. I have to tell it some kind of increment step, because if I doesn't get modified, this loop will just run forever without stopping. And then finally, the body of the loop comes last. So this particular one, you can set different values of different things here. This runs, starts at 0, checks to see if I is less than 4, increments I if it's not, and then finally prints I. So for loops can take multiple steps in each piece of the definition, which means we can have multiple initializations, we could have multiple checks as long as it evaluates to a true or false, And so typically chained together with an and or an or. And then of course we can have multiple output statements. So as an interesting example of using that sort of idea, we could do something like for A is equal to the empty set. So we're just immediately going to initialize A to be the empty set. And let's just say for I is equal to 0, and then we'll check to see that I is less than or equal to 5. And then finally we need to increment I. So let's just, I plus plus. And then suppose that the body that I want to do now is append to A, I. And I run that. Well, what is the output going to be? Well, I can check. And if I do check and I see what the output of my operation here is, my loop, what I've gotten is this loop has run. It started A as the empty set. It ran from I is equal to 0 to 4, incrementing by 1, and at each step, it took the value of I and glued it into the set A with the append to command. So you could see that, there's different ways we could do this. We could actually plus equals 2 in here. And now if we check A, we get 0, 2, and 4. So what did I actually do? What does this plus equals increment mean? That says take whatever the value of I is, add 2 to it, and then set that equal to the new value of I. So this is equivalent to the statement I is equal to I plus 2, but written in the language of increments. If I like, I could actually, let's pull this back to plus plus. Suppose I wanted to print the value of A at every step. I could do that again, separating separate statements with semicolons, and that will show me how A is built up as the loop runs. It starts at the empty set, then 0 gets appended, then 1 gets appended, then 2 gets appended, then 3 gets appended, and so on. The advantage of using a for loop here is that every time I run it, A gets reinitialized to being the empty set, instead of me having to go back and clear all the variables again. I can just say what I want A to be equal to right out the gate every time this loop executes. So let's talk a little bit about nested loops. And a nested loop is just a loop that sits inside of another loop. So a very primitive way of setting something like that up is, say, a do loop inside of another do loop. So I've got one do loop that runs on the inside, incrementing on I, but then that runs for each time the outside loop runs, incremented in J. And if you run that, you'll see that the output that we've printed here actually shows what the order of increment is. The first thing that happens is J is equal to 1, and it sits on J equals 1 while the inner loop runs. So while J is equal to 1, the I loop increments from 1 to 2. Okay. Another example here would be to do something where instead of having multiple do steps, a do loop is perfectly happy to take each index that you're after and just, if you give it more than one index set, it's going to treat each one of those things as a separate implementation of the do loop. Now, you should notice that the outputs are different. And the reason that the outputs are different is because it's evaluating them in order now, the outside loop is the first entry and the inside loop is the second entry. So what this one is doing is it's saying fix I is equal to 1, and then for I is equal to 1, produce all these values of J, so 1, 2, 3. So the outputs are the same, but the order is backwards. So that's just something to be aware of. It does actually matter in some cases. So table, which we've been using all the time, is actually just a specialized do loop where instead of being able to put anything I want up in here, what table does is it's burying anything that you do inside of a big list. Okay, so table is specifically a do loop aimed at creating lists. And the virtue of that is that I don't have to do awkward constructions with append or append to or setting a set equal to a union of a set with something else. I can just do it with a table. So let's actually look at the approach that we would take in a structure like this for finding, say, all the Pythagorean pairs for values of m and n that are less than 100. So a Pythagorean pair is the two numbers that are the legs of a Pythagorean triple. So 3 and 4, for example. So 3 and 4 is a Pythagorean pair because 3 squared plus 4 squared is equal to a perfect square. In this case, 5 squared. Okay. And so what we want to do is to be able to check all of the pairs m and n that make this true for values of m and n that run from 1 to 100. Oops. Pair. There we go. Okay. So another way of phrasing that 3, 4 is a Pythagorean triple would be to say that the square root of 3 squared plus 4 squared is an integer. More useful condition for checking something like that. So our approach for using sort of a nested loop structure is that we're going to use a table that we generate on 2 indices, which maybe that doesn't quite feel like we're working in the language of loops. But remember, a table is just a specialized do loop. We're going to use table with multiple indices to produce all possible pairs m and n. And then we're going to check each entry in that table to see if it fits the condition that if I square the 2 entries, then I get an integer out the other side. So the first thing I'll look at is what table will do in this setting. So if I did a table, say I produce a table, and I'm trying to do tables that look like I and J, right? I need pairs I and J so I can feed them into some kind of check to see if these things are Pythagorean twin or not, or Pythagorean pair. So I'm going to say, let's just look at a table that's 3 by 3. It's supposed to be I. And put a J right here. So I've got this list now of all of the pairs that involve 1 and 3. Of course, if I'm plugging these into a symmetric expression like m squared plus n squared, the problem is that I'm doing a lot of repetition here. I don't really care about the order that these pairs appear in. And it doesn't seem like a big deal when you're working at a small scale, but when these things start scaling up and you get these big arrays or squares or rectangles of numbers, it actually matters for computational time if you can start stripping out repetition. One way to reduce the repetition in this list, eliminate it in this case, is to let the outer loop run from 1 to 3, but the inner loop run from I to 3. And in that case, we're just going to get the unique pairs up to symmetry. So we don't have 1, 2, and 2, 1 on the list that comes out. We just have 1, 2. So these are all the pairs where order has been removed. Now I've got a list of all the pairs where I run from 1 to 3. If I want to go from 1 to 100, I could just put 100s right here and right here, which is what I'm going to do. And I'm going to suppress the output because I don't really want to look at a 100 by 100 matrix. If I had a pair, how could I check to see that it's a Pythagorean pair? So I'm going to need some sort of condition that I can use to detect that. And it needs to be Boolean. So one way of doing that would be to write down something like integer q. So if we did an integer q, and the thing that we were looking at was the 3 and 4, how would I use integer q to detect that 3 squared plus 4 squared was equal to 5 squared? Well, I'd probably use something like integer q of the square root of 3 squared plus 4 squared. If I run that, I get true because 3 squared plus 4 squared is 5 squared. So if I put in the 3 and the 4, then what I end up with is precisely what I wanted. 3 and 4, add 3 squared plus 4 squared, add to a square number. So when I take the square root out, I get an integer. I would like to use this idea as the logic check on a big select command. So I could do something like, well, let's take this out, and let's take this out, and let's make it into an anonymous function. But what are we going to be getting out of this table? We're going to be getting out these lists out of the table. And in fact, maybe what we should do is we should drop those inner rows here. So we just get a list of points down. So if I took this thing and I flattened it to level 1, I should just get a list of coordinate pairs, which is exactly what I need. So now I've got a condition that will run on a coordinate pair. So what I can do is I can use this as part of a select command. And what we should see when I do that, so if I select over the table that I produced, so this thing right here, in fact, let's give this a name. Let's call this A, and let's say that we're going to flatten the table And we can check A real quick to see what it looks like. Okay, so A is a list of... Oh, I didn't need to flatten A. Oh yeah, flatten your list to the right level. There we go. I flattened all of the braces out, and I really just meant to flatten the rows out of this because I do want a list of coordinate points. Okay, so be careful when you're flattening, right? Okay, so now I want to select over this list of coordinate pairs A, and I want the selection function to be this guy. If I run this, I end up with what looks suspiciously like the Pythagorean triples. 3, 4, which result in 5, 5, 12, which when you square them and add, you get 13, 6, 8, and so on. And so this list that we've created here, this is the list of the legs of the Pythagorean triples. There's going to be an exercise based on using this list that you're going to be doing as part of your homework. But the idea is that at the bottom of this is the use of a double table, or is the use of a nested loop to create the table, because our logic here was thinking of this as a nested loop. The reason that we can do one index from 1 to 100 and a second index that depends on the first index is because by using two indices, table is really acting like a double loop, a loop inside of another one where the outside index increments, and then it runs over all of the possible values of the second index before it increments the first index again. There's your basic loop structures, including nested loops. What we're going to talk about next time is going to be, one of the topics we're going to talk about is actual nest command. And what the nest command is a way of doing is repeatedly applying function composition. We're going to talk about fold and folded lists. And then we're going to talk a little bit again about inner and outer, although just a little bit because you guys are already familiar with that. So with your basic sort of loop structures in hand, you can get started on a lot of the questions from chapter 7. And I am looking forward to seeing your answers to these. We're getting to the part of the course where the creativity that you bring to these exercises means that I get to look at a lot of different solutions to the same questions. And that's a lot of fun. So take care, and I'll see you in the next video.